Okay, folks, we are going to work on chapter 3, lesson 7, which is going to be translations and reflections of linear equations. We're going to focus on two things. First is that you can translate and reflect graphs of linear equations, and then you're going to also be able to stretch and shrink those same things. Okay, family of functions is a group of functions with similar characteristics. The most basic function of the family of functions is the parent function. So for our linear functions, the parent function is going to be f of x is equal to x. So just slope-intercept form, slope of 1, y-intercept of 0. The graphs of all other non-constant linear functions are transformations of the parent function. Okay, remember that a transformation changes the size, shape, and positions and orientation of the graph. Okay, the first we're going to deal with is horizontal and vertical translations. Okay, so we're going to deal with a lot of things in function notation today. So the graph of f of x is going to be translated by adding or subtracting a k value to the graph. Okay, and then similarly, we're going to have horizontal transformations by adding or subtracting an h value on the inside of the function notation. And we're going to see what that looks like. So let's go ahead and do the first one. So here I'm going to let f of x is going to be 2x minus 1. And what we're going to do, we're not actually going to graph it by hand so much as just see what the difference is today. But we're going to let there be a new function, g of x, and it's going to be equal to the original f of x function, but then we're going to add 3 to it. So that's what all 3 of those parts mean. So all we're going to do is a little compare and contrast, and we're just going to write about the differences we see. Okay, so we are going to go into decimals here, and we're going to have f of x is equal to 2x minus 1. Oops, forgot the equal sign. Okay, so our graph starts with y-intercept of -1 and then has a slope of 2. So that means we're going to go up 1, 2, right 1, up 1, 2, right 1. Okay, or down 1, left 2. So now what we're interested in is what happens if I take and create a new function, g of x, and that is going to be equal to the original function, f of x, but then I'm just going to add 3 to it. So let's see what happens. Here's red's our original f of x. Okay, so if we take f of x plus 3, red line to blue line, it looks like it's just taking it up from the y-intercept of -1 to a y-intercept of 2. And has the same slope. So it's basically the same thing. It's just been moved up 1, 2, 3 units. So what has this done so if I have an original function, f of x, and I am transforming it in a way that I have a new function, f of x plus 3, all that's going to do is going to move it up 3 units. And that's exactly what this diagram down here is showing is the same thing. Okay, so now what we're going to do is we're going to do the exact same thing, but instead of f of x plus 3 on the outside of the function notation, we're going to do plus 3 on the inside of the function notation. So again, let's see what that looks like here in the graph. So we have our original f of x, but now we have our new function, and I think the new function is going to be called t of x. So function name t, variables x. And what it's going to be is it's going to be the exact same thing as f of x, but instead of plus 3 on the outside of the function notation, it's going to be minus 3 on the inside of the notation. So what did it do? It looks like it has the same slope, but what did it do is it took any of our points, and what it did is it kind of just shifted it to the right. It's like the same graph, but we've just moved it from 0 to 1, 2, 3. So this actually just moved it to the right 3. So starting here, right 1, right 2, right 3. So we can go ahead and categorize that. All right, so if I have a function f of x, the original function f of x, and I translate it in a way that I go f of x minus 3. Notice there's a big difference between -3 on the inside and +3 on the outside, or +3 on the inside and +3 on the outside. Those are two different things. And actually, it's a little bit backwards, and I'll talk about why when I return, that this will actually move it to the right 3. Now, I know we think -3 would move it to the left because we associate moving to the left with negative and right with positive, but this is just honestly a little backwards. Okay, so if I take a function f of x and I -3 on the inside of the function notation, it's going to move it right 3. If I take a function notation and I add 3 on the outside, it's going to move it up 3. So we can categorize this. If I take any function f of x and I transform it in a way such that I'm taking that f of x and I'm adding a number on the outside, can't reiterate this on the outside, that will move it up, whatever that number is. Okay, whereas if I take my function f of x and I transform it in a way that I minus a number on the outside. So if I plus a number on the outside, it moves it up. If I minus a number on the outside, well, it's going to move it down, whatever that number is. Okay, so now what I can do is I can do the same thing, but now we're going to talk about what happens if I take my function f of x and I transform it in a way that I add 3 or add a number on the inside of the parentheses. Again, hopefully you can identify the difference between being outside of the function notation and now we're inside the function notation. If I add a number to on the inside of the function notation, that will move it to the left, whatever that number is. If I take that function notation and I transform it in a way that I get f of x and then I minus that number on the inside of the function notation, well, adding it on the inside moved it left, adding it on the inside or minusing on the inside will move it right, whatever that number is. Okay, so that's the whole first page. Honestly, if you struggled with some of this, maybe just rewind it and watch some of the parts over and see if you can start to pick this stuff up. And if you have questions when I return, I'll answer as many of those as I can. So now what we're going to do is talk about reflections. So you want to think about reflections like when you look in a mirror. If I am looking in a mirror and I am 5 feet from the mirror, the person in the mirror is also going to appear to be 5 feet from the mirror. So the distance from me to the mirror, the spot of reflection, and the person from the spot of reflection and the person in the mirror is the same distance. Okay, so what we're going to talk about is actually the graph when I take a minus sign on the outside of the function notation and when I add or put in a minus sign on the inside of the function notation. So what those are going to do are two different things. Remember, f of x is just our y value. So if I put a minus sign in front of it, whatever our y value is, we just take the opposite. Where here, this one here on the right, if I'm putting the minus sign of the x, I am taking whatever the x value is, I'm taking the opposite of it now. So if I plug in x is 3, well, now I'm using -3. Okay, and so that creates a little bit of different things that happen. So again, when I'm reflecting over the x-axis, I'm multiplying the outputs by -1. And when I'm plugging it in the inside, I'm multiplying the inputs by -1. And this causes a reflection. Okay, so we are going to use this f of x is equal to 1/2 x plus 1. And the very first thing we're going to do is we're going to look at the graph of g of x, but g of x is going to be the opposite of f of x. So let's go ahead and see what that looks like. So 1/2 x plus 1. So here I have f of x will be equal to 1/2 x plus 1. So again, in slope-intercept form with a y-intercept of 1, and I'm going to go up 1, right 2. Up 1, right 2. And so now I'm going to take that g of x and I'm going to make it equal to the opposite, so I'm going to sign, of f of x. So what did it do is it reflected it over the x-axis. We can see this because look, this point here is 1 to my line of symmetry, which is my x-axis, and then the point on the other side is 1 away. Here, look at this point. This point is 1, 2 to the x-axis. The point above is 1, 2 away. Same thing back here. This spot is 1 away from the x-axis, and then this point is also. It's important to note that they have the same x-intercept, so the x-intercept stays the same. So let's go ahead and look at this problem here. So what happened? Well, if I take my function f of x and I translate it in a way that I take the opposite of the f of x, okay, what is that going to do? That is going to reflect over x-axis, okay? And it's important to note that the x-intercept will stay the same. Okay, so again, this here, what we just did, that's when I have the minus sign on the outside of the function notation. If I have the minus sign on the outside of the function notation, it's a reflection over the x-axis. Okay, so now as I look at this here, we're going to do the same thing, but now I am going to have a function called t of x. And t of x is going to be the same as f of x, but instead of just plugging in the x value, I'm going to plug in the opposite of whatever x value I have. So we're going to look from green line to purple line. So what happens here is we have a reflection over the y-axis. So as you can see here that my y-intercept is staying the same, but here, look at this point. This point is 1, 2 away from my y-axis, and the point on the other side is also going to be 1, 2 away. You can see that up here. This is 1, 2 to my axis, or kind of like an axis of symmetry, but 1, 2 my y-axis, and then 1, 2 away. So it's just taking the line and just mirroring it over on the other side. So what does that mean? If I have a minus sign on the inside of my function notation, that causes a reflection over the y-axis. Okay, so we can do the same thing that we did here. So if I take my f of x function and I translate it in a way that I take that f of x, but I just use the opposite of whatever x value I originally had, that is going to be a reflection. I don't know why this is all caps. This is going to be a reflection over the y-axis. Okay. Also important to note, the x or the y-intercept will stay the same. Okay. And that is reflections. There's really nothing else for me to categorize because there's not another direction. It's either minus sign outside of the function notation, reflecting over the y or x-axis, negative sign on the inside of the function notation, reflecting over the y-axis. Okay, so we're going to transition into the last one that we're going to have. But before we do this, I actually forgot. What I want you to do is pause the video. And what I want you to do is everybody kind of off on the side like we normally do, just work on 1 and 2. You don't actually have to graph. I just want you to describe the transformation from one graph to the other. Okay, so I am assuming that you have already taken the time to work through these problems. So I'm going to highlight this one here in blue, and I will do my blue work off on the side. Okay, so here, number 1, we have a function f of x. And when I am translating it, what I'm doing is I am translating it in a way that I'm doing f of x minus 2. So I want to know, what does this do to my graph? And what does this do? I'm minusing 2 outside of the function notation. This is going to move my graph down 2 units. Okay, so then there's also another one. I guess this is g of x is equal to. Okay, so now we're going to take that same thing, and now we're taking f of x, the original f of x, and we're kind of translating it into a new function, h of x. Okay, and h of x is going to be equal to whatever f of x is, but now I'm minusing 2 on the inside of the function notation. So this will change what it does. Okay, it is going to translate it by moving it to the right 2 units. So again, inside will move it left or right, outside will move it up or down. And whenever it's on the inside, it's just, honestly, it's just a little backwards. Okay, now I'm going to do number 2, and we will do number 2 in green, I suppose. Hopefully I have green ink here. Okay, so now we're going to do number 2, and there is green ink. Okay, so now I'm going to do number 2. We have our original f of x function. okay? And we're translating it into a new function called g of x. Okay, and g of x is going to be equal to the opposite of whatever f of x is. Okay. And what is that going to do to the graph? Well, we look up at your notes here. It is going to reflect it over the x-axis. Automatic lights went off. So, all right, and so that's all it does. It doesn't do anything else. It's just a reflection over the x-axis. Okay, and then the second half of this is now we're taking f of x and we are translating it into a new function called h of x. And h of x is going to be equal to f of x, but instead of regular x values, I'm going to use the opposite of whatever x value I have. So what is this going to do? I have a minus sign outside of the function notation. It reflects across the x-axis. If I have a minus sign on the inside of the function notation, it is a reflection over the y-axis. And I can't type today. All right. And so those are the two problems. So exactly these four type of things, 1, 2, 3, 4 is exactly what you're going to need to know how to do from this section. So again, if I look at the top though, you need to know what happens if this here is +2 or -2, and same here, +2 or -2. These ones you just have to check, where's your minus sign, inside or outside. All right, now we're going to move on to the last one, which is going to be horizontal stretches and horizontal shrinks. So essentially a horizontal stretch is taking the graph and stretching it away from the y-axis or shrinking it back towards the y-axis. A vertical stretch is taking it from the x-axis and stretching it away from the x-axis or shrinking it down to the y-axis. And those two things are the only things that you really need to know how to do from this section. Okay, so here we are going to have a function called f of x, and I need the highlighter. It's not working. Okay, here we go. And that is going to be determined by, I have no idea why this isn't working. Okay, whatever. Okay, so either way, I am going to take it and you're going to stretch or shrink by multiplying the function by a number on the inside of the function or the outside. So first, what we're going to do is we're going to talk about when I multiply. I take my f of x and I'm going to translate it to a new function called g of x, which is going to be equal to f times and then 1/3 x. Okay, and this 1/3 is being multiplied on the inside. So we're going to look and see what does that do when I multiply it by a number less than 1 and by a number that is bigger than 1. So let's go ahead and pull up the graph. So here, my original function should just be, I think it's x minus 1. And now I have a new function. It's going to be called g of x. Okay, and it's going to be equal to f of 1/3 of x. So let's see. Green is the original function. So we have an x-intercept of 1. And f of x, or g of x, my new function, has a function of an x-intercept of 3. So look, how far from the middle line did it take it? From the y-axis. So when this number is less than 1 and greater than 0, it takes my x-intercept and it stretches it away from the middle y-axis. So this is a horizontal stretch. So as you can see, if it was when it's just f of x, you can see we're going to see the purple line move. When I type in 1/3, it stretches it off to the right. Okay, so what does this do exactly? This is going to be a horizontal stretch. Okay, but so now I'm going to kind of make one up on the fly here. And what if I take g of x and let's call it t of x. And I'm going to take that f of x, but instead of 1/3 x, I'm going to do 3x, so like a big number. Let's see what happens when it's like a bigger number than 1. Okay, so here I'm going to change it. So here we're going to look what happens to the purple line. Green line will be remaining. And when I go 3, we'll look at the x-intercepts again. It goes from 1 to 1/3. So it took it and it actually drug it in towards the y-axis. So this is actually a horizontal shrink. It's moving it in towards the y-axis. So again, this is a shrink. This would be a horizontal shrink because it's moving that x-intercept in, which is horizontal. Okay, so let's categorize this because I think we're going to do these separate. Okay, so if I take a function f of x and I translate it in a way that I now have f of a times x, we need to consider what is a. So if a is between 0 and 1, which would be this inequality. So you might see the text that you have called this. If a is between 0 and 1, okay, this is going to be a horizontal stretch. Where if a is greater than 1, the inequality would be a is greater than 1. Okay, this is going to be a horizontal shrink. And I spelled horizontal wrong. Okay, so here, this right here is going to be kind of the big thing. So this is when a is on the inside of the function notation. Okay, this is when a is on the inside here. You want to remember that there's a difference between the a value on the inside and then the a value on the outside. So now let's look and see what happens when the a value is on the outside. Okay, so now what we're going to do here is kind of the same thing. We're going to have a function f of x, and we're going to translate it in a way that I now have a new function h of x, which is equal to 3 times f of x. Excuse the bell. And let's see what happens. Okay, so now instead of this 3x on the inside, I'm going to have a 3 multiplied by the function on the outside. Okay, so what's going to happen is you want to look at the y-intercept to see what happens. Okay, so the x-intercept stays the same. And what happens is it takes it and it stretches it away from 0, 0. And that's a good way to think about it, stretching it away. Which way is it stretching? It's stretching in the y-axis. So that's a vertical stretch. It's taking the y-intercept and stretching it away. Okay, so this is going to be referred to as a vertical stretch. Okay, what if I take f of x and I translate it in a way that I have a new function q of x? Okay, and that's going to be a decimal. So let's say something less than 1, so 0.5 times f of x. Okay, so something on the outside that's less than 1. Okay, so you might have already been able to guess, right? We have a horizontal stretch, a horizontal shrink. Well, this one go from a vertical stretch to a vertical shrink, and let's see that happen. Okay, so here I'm going to replace this 3 with a number less than 1. And as you can see, right, it goes from -1 to a half. It's getting closer to the origin. It's shrinking towards it. Okay, so here I'm going to get rid of this. Here, that's where it's regularly at, and then 0.5, shrinking it towards it. So exactly like I said, that is shrinking it towards the y or the x-axis. So that is a vertical shrink. Okay, and so then let's go ahead and categorize this. If I have a function f of x and I multiply the outside of the function, I guess we need to put I'll put an asterisk there. That means multiplication. Okay, so if I take a times f of x, you have to look. A is between 0 and 1, meaning that 0 is less than a, which is less than 1. What is that going to do? Okay, that is going to be a vertical shrink. Okay, what if my a is greater than 1? Okay, what if a is greater than 1? What's that going to do? It's going to be a vertical stretch. Okay, And again, you need to be careful because this here is different than the one above because this A is outside. Okay, there's a difference between the A being outside of the function notation and inside the function notation, and the differences are right here. Okay, and these are the differences that you need to know. Look at that, great box. Okay. So that's kind of the lesson. Okay, so not a whole lot left to cover. So what I want to do is I want to go down to the homework, and I will assign our problems. I gotta get it out of the folder here. 1 second. Okay, so your assignments are going to be problems 5 through 10. So 5, 6, 7, 8, 9, 10. Okay, and all you have to do is describe the transformation. Right to, reflect over x-axis, reflect over y-axis, things of that nature. Okay, also 13 through 22 odd. So 13, 15, 17, 19, 21. And then 29 through 34, all of them, 29 through 34. Okay, that is all of these down here. Again, these are all just describe the transformation. Translate up, left, right, down, reflect over x-axis, reflect over y-axis, horizontal shrink, horizontal stretch, vertical stretch, vertical shrink. And that's it. Those are the only things that I'm going to ask for you to know. Okay, so make sure you work on this while I'm gone, because when I come back, we're going to build on this same stuff and try to finish out the rest of the lesson to hope that you have a good understanding right off the bat, to make sure that you, because of what we're going to add on to it is what I'm trying to say, is we're going to add on to it. So you have to have these foundations to make sure that you're ready to go. Otherwise, you can work on these problems. And then when you're done, you can work on any missing work. There's plenty of that for all of you to go around. Otherwise, I hope you have a good weekend, and I will see you next Tuesday. Okay, goodbye.